So let's get started. What materials, in my opinion, have the specific strength relevant to the space elevator tether? So I looked into this and decided that single crystal diamond, cubic boron nitride, graphene, hexagonal boron nitride, carbon nanotubes, possibly boron nitride nanotubes, and all of these are very interesting materials, but now in September, we have single crystal graphene and single crystal monolayer HBN or few layer HBN. So I'm going to focus on what we have in hand in this talk. Okay, so what's the mass of a 100 million meter long, 1 meter wide, so 100 kilometer out, 10 micron thick, density the same for HBN and stacked graphene, density of graphite? Well, the answer is it's 2,260 metric tons. And if that were a laminate of graphene, it would have, or HBN, it would have about 30,000 layers. And if we use the density of single crystal graphite, we can get a particular number. So currently in the world, we manufacture roughly 3 million metric tons of synthetic, and we mine 1 million metric tons of natural graphite powder. So we currently can make single crystal graphene and single crystal HBN. We can grow them epitaxially on certain metal 111 substrates, nickel, copper, copper, nickel. And the same for single crystal HBN, including several layer. We can grow, as our group has in collaboration with Professor Hyun-Suk Shin, on nickel 111, and I'll show the publications later. And then we'll also see that there are possibilities about growing on liquids, like liquid copper. Now, currently, what we in the community do is we grow these single crystal layers and then we cool from the CVD growth temperature, somewhere around 1,000 degrees C, down to room temperature, and then we manipulate and play with liquid solvents and so on to delaminate. There's been a lot of very nice work. The films, but this is incredibly slow. So for making the quantities we need for something like a space tether, this is showstopper, in my opinion. So we have manufacturing issues, and if we were to consider that we make this material at a meter per second and transfer and lamination works, this would be 3.17 years. This is only monolayer single crystal graphene. It's not the 30,000 layers that we need. Houston, we have a problem. So chemists refer to the rate determining step in manufacturing terminology like bottlenecks are used. And my face is in the way, but this little guy says, look, we found a bottleneck. So what I propose is a new research effort needs to be started on peeling at or near the growth temperature, ideally, so we don't slow things down by cooling down to room temperature and then warming back up. And this could be as noted on those metal 111 surfaces, or it might be from a liquid metal. And then the roll-up or lamination should keep pace with the peeling, otherwise it becomes a rate determining step. In this talk, I will assume that it is keeping up with the peeling. So why am I ignoring growth rate? Oh, I'm not. Uh, I'm assuming some engineering advances. I think they can be achieved. So let's talk about how much we have to grow, given that we have to peel quickly to get enough of the material. So if we really needed to, we could make probably a 1 meter wide nickel 111 surface enclosed in a chemical vapor deposition environment. It might be very, very long. It might be even a kilometer in length. Then we grow everywhere simultaneously. So what growth rate yields complete coverage of, for example, N-layer single crystal graphene or single crystal hexagonal boron nitride, and what is the value of N? So we need to find, I think, pretty obviously, monolayer is not going to get us there unless we have a whole lot of factories producing monolayer and laminating. So what we need is we need also synthetic roots to N, where N could be 2 or 3 or even larger. And it's exciting to see in this year, 2025, we've had a few papers appear. Recently, a group at Harbin Institute of Technology used liquid copper and they could grow up to 5-layer in one run. Single crystal is what is reported over, I believe it was 3-inch wafer size. So this is very intriguing. And liquid copper would be a lot cheaper, I think. It would have to be kept very pure. Can't let oxide slag grow on its surface, etc. But this is very interesting. And then in another paper, this time from the Beijing Graphene Institute growth, they came up with a method to grow up to 7-layer, apparently single crystal graphene. Now, I think for both of these papers, the obvious thing that needs to be done from my perspective is we need to make macro scale mechanical measurements on the N-layer samples because there is the question, have they properly stitched together or not? That is to say, islands grow by nucleation in different locations and then they either grow together very perfectly or they don't. If they don't, it's going to be mechanically weak and not work. So that's a very exciting opportunity. We'd love to be involved. We're good at macro scale, single crystal graphene measurements. Now I'd like to show a little video that I made. We bought this little breadboard, and this is purely conceptual, like thinking big loops of metal 111. Doesn't have to be in that configuration. Okay, here's a little buildup of the RSR production loop. The loop, the big loop, is shaped sort of like an oval here. The growth stages can be as long as we want, up to 1 kilometer. Eventually it's got to make a loop. And I'm showing HBN, so it's white, being peeled off downstream here. This worker fell over in frustration because you can see it's slightly delaminated here. Maybe not a good thing. And here's our pickup. Somehow we peel effectively, and then we imagine that this is spooling up here. We might make it an oblong spool to fit onto this giant Falcon X rocket that chat tells me can SpaceX can send it to geosynchronous graphics and fun videos. Okay. Okay, so that was purely conceptual, and maybe a continuous loop of material could be generated that is constantly in one region having HBN growing on it or graphene, and then that growth region probably pretty long. And then we're going to bring it over to where we have a peel line. So what do we mean by a peel line? Well, let's look at a few videos here that Miri made. We notice in the second video that we're applying some additional lever, like blowing argon gas or something. So anything that can speed up the peeling and have it work well, we, not have it interfere with the properties, not have contamination, etc., is of interest, and I think should be pursued. So our focus will be on the peel line. So sort of showing again, you see the peel line, and these are meant to be conceptual also. The peel line might stay stationary, the platform might move underneath, or we might peel with some sort of device that runs along the growth substrate. So what sorts of methods could be used to perhaps increase the peeling rate? Here I'm just tossing out some possibilities. I'm not claiming this is a complete list or even the right things to do. So let's consider growth time and rate of peeling. So let's say we've got a setup that we can grow well on, whether it be liquid metal or M111 surfaces, and we're going to grow our single crystal, but it takes 200 seconds. So if we want to peel at the rate that Usain Bolt runs at, then we are going to have a several kilometer long growth section that we then run around and peel all of it, or it moves in some manner past the point where we're peeling. Now, with Usain Bolt's pace of peeling, we then have the consideration that 100,000 kilometers with separation and transfer, not limiting, just the peeling is limiting, okay? So this is a big if. Then we're talking 1% of the tether maths being made in 1 year. And this is doing as well as we can. So that's monolayer though. So I'm sorry, this is 10 layer. So that's monolayer would take 10 years. So even at 10 layer, we have to be really thinking about the scale here. It's a fascinating challenge. So time to put our hard hat on, I think. If this is going to be done, it's going to have to be done on a really significant scale of manufacturing, which is fascinating. So in our center, we're the Institute for Basic Science, we need to also do basic science. So I can tell you, I don't find anything on peeling, particularly peeling at high temperatures. There are a few nice studies of peeling of polycrystalline graphene, for example, from copper surface at room temperature, but high rate peeling and being close to the growth temperature, maybe dropping a little bit so that the surface is still stable. But liquid copper, we'd have to make sure that it remains liquid, melts at 1085 degrees C. I don't know whether peeling can be done from liquid copper or liquid metals. And I don't know whether peeling can be done at these rates from the M111 substrates But I think it will be much easier to peel if we have multi-layer than we have monolayer. I'm just going to show you some visualizations that colleagues from the design department at UNIST, students Danielle and Alina and Professor Kim, have made. I won't say too much about these other than they're purely conceptual. They're just meant to sort of convey something happening on a large scale. And this is similar to what I had showed before. This is maybe an argon gas helping the peeling in some manner. This is, we might combine lamination and peeling in some manner. That's very efficient. We might have large surfaces that actually move. I think it's probably better that they be stationary. We can run a roller around, but there are people much more expert in manufacturing than I am. So I'd like to acknowledge and really express my appreciation for discussions with my team members that are shown here with their names in blue text, and then colleagues in Italy uh, at the University of Trento, and then also the colleagues at UNIST in, for example, Sunyoung Kwan and Jae-won Kim. Uh, Professor Kwan and his student Jae-won have been growing very nice single crystal double layer HBN on nickel 111. We would like to work with them. And I think that the conversations with Dr. Usaf and all of the ISEC colleagues that took place actually 6, 7 months ago, very intensively, longer, 9 months ago, brought me up to speed on space elevator issues, but I am not an expert in the space elevator. I kind of zoomed in on just today's topic. So what I'd like to do now is just show some additional slides so that the viewer can see a series of papers listed that seem relevant to the topic. And since this is a recorded talk, I really won't say anything about those. I'll just show them for 10 seconds each. I won't be here for questions, so my email, ruofflab@gmail.com, was listed on the first slide. So this is a little bit about rockets, which I don't know very much about. How are we going to move stuff from Earth up to certain orbits? Yeah, it's very interesting if we wanted to make C12 pure, which is not that hard. It's not that expensive compared to natural abundance. The thermal conductivity goes up dramatically, both for graphite and for graphene. Multilayer graphene, that will certainly be true, in case that's useful. For BN, we can isotopically label the boron. Nitrogen's already very pure as nitrogen 14. It helps. Two different elements, it's going to be lower thermal conductivity than graphene. And this is a paper in review. We're just on the verge of submitting response to reviewer comments and our revised documents to a journal. But this shows that the macroscale single crystal graphene is indeed looking very promising for space applications, aerospace applications, for light weighting in general, and also for the space elevator.